Good morning. Today we are going to start this Jordan curve theorem. Suppose X be your topological space. This is topological space, and by a curve in X we mean a continuous function. So this is your curve in X. By this curve we mean a continuous function. Let that function be gamma. This is a function from closed interval AB to this topological space X, where A and B, these are real numbers, and A is less than B. So let's have this point, that is your initial point. So gamma at A, the first point, that is A. So gamma at A will be your initial point. And the value of gamma at this B, that is your final point or terminal point. That is the ending point of the curve, and the curve is said to join these two points. Now if we're going to look at the image of this closed interval AB under this gamma, which is continuous, that is the image of closed interval AB under this continuous function gamma, that image will be gamma of t, where t lies between this closed interval AB, that is t is greater than equal to A and less than equal to B. अगर ये इक्वालिटी का साइन यहाँ पर इसके साथ है, दैट मीन्स आप क्लोज इंटरवल यूज़ कर रहे हो. अगर इक्वालिटी का साइन हट जाता है, देन योर इंटरवल विल बी ओपन इंटरवल. Since I am considering this closed interval, that is the function is defined on the closed interval, so this equality is included. Okay. Now when the curve is said to be closed, or when the curve is said to be simple? Closed and simple. So the curve is said to be closed if these 2 points join together. That is, your gamma A should be equal to gamma B. So if the curve is said to be closed if gamma of A is equal to gamma of B. Now if the curve is said to be simple if gamma is 1, 1. What is 1, 1 function? If we take 2 distinct points, then A and B, that is, if we take 2 distinct points, then the value for the point A, that is gamma of A, should also not equal to gamma of B. Then your curve is said to be a simple curve. Closed curve is like this. Your initial point, that is gamma of A, ends at this point, that is gamma of B. Your terminal point and initial point are same. But in case of simple curve, if this is your gamma of A, then your curve may be like this. This is your gamma of B. So this is your simple curve where these 2 points do not meet. So this is also your simple curve in this topological space X. So now is the Jordan curve theorem. So there is a note over here, that is, okay, if you look at this geometrically, that is your simple curve. If you look this as geometrically, then your curve should not intersect itself. So geometrically view for the simple curve is that if the curve does not intersect itself, so then the curve is said to be simple. So there is a note over here that a closed curve on the closed interval AB that is simple on closed interval AB and open point B is said to be simple closed curve or the Jordan curve. Simple closed curve or Jordan curve. Next is some of the examples for these curves. If you look at the example, that is, suppose your curve is like this. This curve is simple and closed because if this is your initial point, then this curve also meets at that point. That is terminal point and the initial points are same. So this is your simple closed curve. Simple इसलिए because this curve does not intersect itself. It is closed, but also this curve does not intersect itself. So this is simple closed curve. The other one, that is, if your curve look like this, then what about this curve? This is your initial point gamma of A and this is the final point or terminal point. Then this curve is simple but not closed. So this is simple and not closed. What about this curve? If I start this curve from here, I end also this curve up to that only initial point where gamma A and gamma B are same. That is, they meet each other. So this curve is closed. Is it simple or not? It is not simple because this curve intersects here at the 2 points, or this curve intersects itself. So this is closed but not simple. At this point, one point intersects at one point will give 2 values. So it has 2 values at this point, or it intersects itself. This curve intersects itself. So it is not simple. Now the example, if I make like this Alright, this is my gamma b and this is the initial point. Now what about this curve? Is it closed? No, it is not closed because gamma a and gamma b do not meet each other or they are not the same. So it is not closed. Is it simple? It is also not simple because this curve intersects itself. So this is not simple. Also, it is not closed. And the last example, if I make the curve like this. Okay, now gamma b and gamma b do not meet. So, and also these 2 points are not equal. So this is not closed. Is it simple? Not at all, because this curve also intersect over this point. So this is also not simple. Clear? So every simple closed curve you see that it separates the two domains, the interior and the exterior one. So we have the Jordan curve theorem now at the next page. That is, if C is a simple closed curve, if C is a simple closed curve, then the complement of C what is the complement of C? If this is C, then this is the complement of C, which exclude this interior. So the outer part is the complement of C. So if C is a simple closed curve, then complement of C consists of two disjoint domains. Two disjoint domains, that is, one is bounded and the other is unbounded. A bounded domain is called the interior one. That is, bounded one is your bounded domain. That is the interior of the curve or interior portion. And the other one is unbounded one. That is the exterior portion. Unbounded domain, that is the exterior portion. So the curve C is the boundary of the each domain. This C is the boundary. This C is your boundary of each domain. One domain is inside, that is your interior, and the other domain, that is the unbounded one, is the exterior. And this is your curve C, which is the boundary for these two domains that are disjoint. So this is all about the Jordan curve theorem. The next concept is about simply connected domain. That is also the interesting one. Alright, simply connected domain, that is a domain D. Let's first write down the definition. A domain D is said to be simply connected if each simple closed curve contained in D, अगर आपकी हर simple closed curve D में ही हो, that contains only the points of the domain inside. So if each simple closed curve, your curve should be simple and closed, contained in D, contains only points of D inside. सारे के सारे D domain के points उसमें include होने चाहिए. And if you see the geometrically view, then a simple connected domain, it has no holes inside. A simply connected domain has no holes inside. Like this, if you have the simply connected domain D, it should cover all the points. The simple closed curve should cover all the points inside of D. This whole portion should be colored. There is no hole in between this portion. So this is your simply connected domain, which contains all these points of D. If there is a simple hole, suppose this, then it is not simply connected. Alright, because it is excluding these points where there is a gap in between this domain. So if you have a look of the definition in the topological side, so the definition will be: a simply connected domain can be continuously shrunk to a point. A simply connected domain D can be continuously shrunk to a point. Suppose like this. This is your simply connected domain. अगर आप इस कर्व को पकड़ेंगे और इसको श्रंक करने की कोशिश करेंगे तो वो और छोटी और छोटी और छोटी होकर एक पॉइंट तक श्रंक हो जाएगी. बट अगर इसी डोमेन के अंदर एक होल है तो इट कैन नॉट बी श्रंक. अगर आप सपोज अगर आप इतना पोर्शन कवर नहीं करते तो अगर आप इसको श्रंक करने की कोशिश करोगे तो इट विल नॉट श्रंक टू अ पॉइंट. So this is your topological view. So next let's look at the example. You see examples. In the first one, this is simply connected domain, and in the second one it is not simply connected, it is multiply connected, and there is a acute phase over here, that is it is also multiply connected where these points are not included. So it is multiply connected. It cannot be shrunk to a point. This example is also cannot shrunk to a point, but the first one, this can be shrunk to a point. Also it contains no holes, it contains holes, and this also contains 3 holes or gaps. So this is what all about simply connected domain. In the next class we are going to start the harmonic function. So this is just a simple concept for just a change in this analytic functions. It is a very interesting one. So thank you all of you, and Thanks for sharing and subscribing. So thank you.